Hi, Solving Science, edition 5, and it's a big one. It's the Hubble Tension. 1929, almost 100 years ago, Edwin Hubble is measuring the universe and he realizes that it's expanding. Now, astronomers have been measuring and trying to define this expansion rate and define what's called the Hubble constant ever since, and they disagree. Primary camps of disagreement are astronomers measuring early time universe, looking back billions of years to just after the Big Bang, maybe about 13 billion years ago, light that's travelled phenomenal distances to reach us, and they're coming in with a Hubble tension value somewhere between 67 and 70 kilometres per second per megaparsec as a recession speed that galaxies are travelling away from us. Then there's the late time astronomers who are using what are called distance ladders to look at another mechanism, to look at much closer phenomena to us and galaxies, much closer range. And they're reaching expansion figures up to 74 kilometres per second per megaparsec. So a conflict which is about 8% of the difference between the two, of the total value. Now that's called the Hubble tension. It's a conflict between scientists who can't agree. And the thing is, they both believe their measurements and data are accurate as the equipment has got better and better. So there must be something else. What can expanse tension theory bring to bear on this? Well, probably quite a lot, because expanse tension theory introduces a density-dependent modulation function as a universe that's operating. So voidy, low-dense space expands quicker, driven by expansion, where mass is tightly coupled to expansion. High-dense regions, that coupling to expansion becomes uncoupled, and again, mass holds itself together and resists expansion. So I can immediately see where there's an opportunity here. Now, I take two passes at this with the two different mechanisms that expanse tension theory has to offer. So the first pass is looking at how the coupling modulation of mass to expansion changes for these early stage and late stage. Now, there are 9 different measurement probes primarily that are looking at measuring the expansion of the universe. Now, I've independently looked at each one. I've applied a standard frozen core parameter set. There's no tuning. This is predictive model. There's a single framework. There's a single application of maths. It's a quantum field theory based theory. It's based on mechanical causal properties of the universe. And the first pass, again, I'll attach the documents, looks something like that. It reduces the Hubble tension by a half. It takes a convergence of the high and the low into a new band of where the Hubble constant could emerge. But it takes this 8% delta down to a 4% delta just by using coupling modulation. Now, how's that working? Well, voids, low density space, the same distances at a given redshift imply the light has travelled over a greater distance for a given redshift, whilst in high dense regions density suppresses expansion and those distances are shorter than traditionally we would have assumed using lambda CMD models. So lambda CMD, lambda meaning dark, dark meaning we're in the dark, we don't know. It's a mathematical cheat code which we're having to apply because we don't know. Now, the second mechanism, expanse tension theory posits expanse tension ripples. Now, think gravitational waves, but with a massive and significant difference. And I'll explain why. Einstein's space-time is actually not a fabric. It's not a medium, it's not an ether, it's not a quantum field. It's a geometric manifold. It has no possessive property to hold, retain energy. It's not an energy store, it's not an elastic. It's the curvature of geometry, but it can't hold or store energy. Now, in my paper on expanse tension ripples, it's like the counter, it's the equivalent of a gravitational wave, but it's a real wave. It exists in a real medium. Now, over hundreds of years, people have been searching for the idea of a quantum material fabric Hubble-based universe. There have been many attempts. So far, they've all failed. Let's see how far this particular quantum field works. At the moment, it appears to be performing quite well. But expanse tension ripples can store and absorb and dissipate and hold energy. It's tiny at local level, but over vast galactic distances, the amount of energy that expanse tension ripples can store in the universe is immense. So applying both mechanisms, coupling and expanse tension ripples, I've applied, again, independently applying expanse tension theory to all 9 probes, and the results are quite startling. Okay. Now, where I've reached is a convergence to a single Hubble constant with a mean of 70.49 kilometres per second per megaparsec, with a standard deviation of only plus or minus 0.08, and I've left the residual tension at less than 0.5%. So what was an 8% problem is now just a 0.5% problem. So again, a real convergence to what could be, and again, expanse tension theory says the Hubble constant, as measured by all 9 probes, is 70.49. Okay, that could help us with various things, including calculating the size and age of the universe, which initial calculations put the age of an expanse tension theory universe at about 13.3 billion years, which actually is in the midpoint between those looking at early time and those looking at late time, which is also where the Hubble tension was probably going to emerge. How does this work? Well, in early time, what happens? The distance corresponding to a similar redshift of light, this elongation of wavelength, must be larger. That low density void of space is driving a much greater expansion of the universe. And that early light has travelled further than we originally thought it had. Whereas the late time galaxies, this light hasn't had a chance to travel through vast voids over billions of years. So the distance corresponding to the same redshift must be shorter. And the combination of those have actually brought into a line all 9 probes of the Hubble constant. So there's a paper, it's published on Zenodo. I'll put a link into this video. Now, implications for a resolved Hubble tension would be enormous. It's one of the biggest problems in science today. My researcher said we have spent and are in the region of about $20 billion globally looking for it and trying to define it across multiple telescopes and observatories across the world. There's about 10,000 people in the world today working on astronomy, including trying to find an answer to the Hubble tension. But what if it's not an astronomy problem? What if it's an understanding of the universe problem? What if we live in a density-dependent universe where the universal voids of low density are expanding at a greater space, a greater rate than the density, heavy density of galaxies? Maybe. Okay, hopefully you enjoyed the video. Please take a look at the document. Please share with friends if you happen to know a physicist, especially a quantum field theory physicist. I'd really like to meet one at the moment. Anyway, either way, I hope you enjoyed it. Bye-bye.